Good morning to all. So I'm very happy to get my friend and collaborator or whatever you can say, Dr. Firman Mangasa with us. Dr. Firman Mangasa is a scientist at the Center of Electronics Frontier, University of Southampton, UK. He received full scholarship for his MSc degree in Mechanical Engineering and PhD degree in Material Science and Engineering from National Chiao Tung University, Taiwan. He has been recently granted the prestigious Mary Skłodowska Curie European Fellowship to run Memristive-enabled neuromorphic system for intelligence in space project delivering cloud servers technology in the sky, that is satellites, space stations, interplanetary probes, etc. He is an expert in the synthesis and catalysis of nanostructured materials, and his research interests are Memristive and sensor technologies, as well as the material processing and analysis for advanced electronics. Prior to joining the University of Southampton, he was with World Premier Advanced Institute for Material Research, Tohoku University, Japan, where he pioneered neutral ions irradiation technique to control the synaptic behavior of Memristive devices. He has published more than 50 peer-reviewed research articles, which include several Nature Electronics papers and conference papers within the last 5 years. Currently, his work focuses on the artificial intelligence hardware accelerator for space and nuclear applications. With this short biography, I'd like to request Dr. Firman to deliver his valuable talk. Dr. Firman, please.
Yes, thank you very much, Dr. Panda. It's a really great pleasure today. I got invited from my best friend, Dr. Panda, to deliver a talk at his university today. So today I would like to share one of our, we can say like an opinion, like a review, like the ideas that we are working on here in the UK. So as discussed as introduction by Dr. Panda, I am now in the UK, joined the Center of Electronics Frontiers. We can proudly say that we are the one of the top group in the UK that leading the AI hardware research. So today we will discuss about Memristive technologies for space and nuclear applications, why we are really confident with the Memristive technologies, and what is the potential and usefulness for this technology can be embedded or integrate or applied for another kind of applications for space and nuclear environments. So let's start with the applications of Redhat electronics. So we call radiation hardness electronic, or we just say Redhat electronics. So it just says like what kind of architecture or devices that can sustain high energy photons or photons or particles, right? Our scope right now is about high energy photons and high energy particles, right? Of course, there are many types of other radiation like electromagnetics and kind of other things, right? But today, the most challenging issue in the space specifically is because of the high energy photons and radiations. So first, we need to know where is the radiation come from and how it can induce damage to our device, to our electronics. So the source of radiations can be from extraterrestrial and terrestrial. Extraterrestrial means from the outer space. So the cosmic events like a supernova, pulsar, star, they emit strong photons and particles towards the planets, including Earth and surface of Earth. In fact, it also affecting the ground of the radiation condition on the ground as well. And Another source of radiations is artificially, like we generate it by ourselves. Like sometimes it is intentionally, like medical and high energy physics experiments where those instruments intentionally produce like positrons or X-rays. Of course, you know that we often take the X-ray test, right, or CT scan or PS scan, etc. Those kind of instruments produce radiations. And another thing is waste product, like nuclear power plants, right? We have radioactive materials. We try to exploit these radioactive materials, but also there is come under the cost, like the waste product of this process. For examples like neutron and gamma ray, like that, right? So let's walk through the applications for its different spectrum, because the applications of electronics, as you can see here in the graph, is really in the schematic is really broad, right? So let me introduce you about the difference of these particles. This is just an example that commonly people describe how a particle or photons can pass through some material, right? Suppose we have the lowest energy particle we have is alpha particle. The alpha particle can simply stop by a thin paper, and second things is the beta particle, or some people also say like electron with positive charge, and we can also say like positrons as well. So these positrons can only be stopped by aluminum foil, and the higher energy ones or photons or X-ray and gamma rays can only be stopped with the lead wall. Well, I cannot say wall, but like a thick lead metal. And the neutrons is one of the highest energies of particles. It can pass through all of these materials, but it can stop by water or concrete walls, like that. And of course, there are many other types of particles that we cannot describe one by one here, especially if you're working in the high energy physics experiments, right, where you created your particles. You collide some particle with another particle, and then you create another new one. That's what they do, and they have their own energy, mass, and they have their own trajectory, and etc. They have their unique damage to electronics as well. One more thing that we need to consider is heavy ions. Heavy ions is also very highly energetic particles, where you can easily damage your electronics. Heavy ions can be like any kinds of ions, like oxygen ions or sulfur or boron or anything, because heavy ions can come from the cosmic rays, because the cosmic event can produce many things, right? Like gamma ray, neutron, not neutron, gamma ray, alpha, protons, especially heavy ions, right? Many kinds of things. And let's start with the space environment. So before we design our electronic, we need to consider where we want to deploy our electronics. So suppose we want to deploy to the space. Okay, which space? How deep is the space you want to go, and how long is the mission, right? So suppose we take a sample for Voyager 2. This is the interplanetary probes, right? So if you can see here, there's schematic how the trajectory of the Voyager probes. There is a Voyager 1 and Voyager 2 here. As you can see, they slingshot or passing by various planets, right? So even though they just passing by through these planets, then they do not need to like just enter the atmosphere or even go down to the surface of the planets. They do not do that, but they just passing by. But even then, we need to consider how the plasma condition around that planetary or the moons, even the moons of that planets. So that's certain things we need to consider. So because we cannot only rely on we calculate the cosmic ray for 10 years of mission should be probably 1 giga gray, for example, right? I just make up a number. So, but when they slingshot or passing by of these planets, they get affected by the environments of that planets, the plasma condition, or even the magnetosphere of the planets. So we need to calculate all of those things, and we can sum up of what is the minimum dose or the energetic particles, how many times that it can hit our devices before it can induce permanent failure, something like that, right? The same thing as we discussed before with the Voyagers. There is one example with the future missions. For example, the Clipper that will be sent to the Europa. Europa is Jupiter's moons, right? So Europa is one of the future missions led by NASA that they are interested in the Europa because Europa has like a water in form of ice, of course, right? So they want to investigate how's the surface conditions and whether it can support some life. So they designed the Clipper probes. They will send there, and what is consideration? This is just, for example, if we send the probes to the Europa, so we need to consider in the Europa conditions, we have proton and beta radiations, high proton and beta radiations, but also we have oxygen and sulfur ions, because the Europa atmospheric conditions or we can say the orbital condition have high heavy ions, right? So we need to consider this. And also our electronics should also consider how strong the magnetosphere of the Jupiter, because the magnetosphere of Jupiter is very high, and then it can also alter how the radiation or how the other particles or ions react in the Europa conditions. That also affect. So the another examples in deep space missions is Mars. That Mars exploration recently get really high attentions, especially from Elon Musk and SpaceX missions, right? So it is quite interesting right now because they try to terraform the Mars and make a Mars like a second Earth. So, but the problem with Mars is it has high protons exposure. It's from the sun. If you can see from the schematic here, even though Earth is closer to the sun, but Earth relative savor low protons compared to the Mars. But the problem with Mars is it doesn't have like a magnetic field to shield radiations from the sun. So radiation from the suns will be the major issues for Mars conditions. So from radiation from the sun also not only expose protons but also X-ray and alpha particles, right? And another things, as we mentioned before about the magnetic shield of the Earth. The magnetic shield of the Earth, fortunately, creates like a belt, radiation belt. We call it as Van Allen belt. There are two belts there, up there, like a Van Allen outer belt and Van Allen inner belt. Their composition a little bit different. For example, like the outer belt is mostly focused, composed of the electrons and small protons, and the inner belt is a bit balanced between electrons and protons and another heavy ions. So if suppose we have some satellites, the geostat, the GPS satellites, and IS space stations, we need to consider that our devices should resistance to the proton and electrons radiations. And it becomes interesting when we goes down to Earth, right? So we cannot avoid the contribution of cosmic rays to the Earth environment. So cosmic ray produce like many kinds of particles, right, as we discussed before, but at the atmospheric conditions, like the ionosphere's upper part of our atmospheres, there's an atmospheric reactions where all of the different kinds of particles are occurred or produced in this sphere. So most of them are neutrons and beta pairs, right? So even though we have like Van Allen belts, we cannot rely on the Van Allen belts because too many high energy particles and strong photons can pass through, still can pass through this Van Allen belt radiations. So that's the reason why we have these atmospheric reactions, right? This atmospheric reaction also produce some cascade effects, like producing another types of particle like pions. And one more thing that recently just got published that in Science, thunderstorm even produce gamma ray. So be careful, guys. If you go outside and there is thunderstorms during raining, just don't go outside too long. So that's the reason. So we can include the gamma ray in the one of the major issue in the high altitude environments. There are similar things that we need to consider for the ground stations. Ground stations means like data server, or even instruments on the ground, like medical instruments, right? So even the probability is low, like only small amount, really small neutrons or alpha particles can pass through and hit the surface or the ground of the Earth. But this small probability still can induce failure to our electronics. Well, for example, probably it can happen. Let's make an example for the autonomous car, for example, right? Probably it can happen. You have some memory electronics there, and then there's a neutron hit your memory array, and it can induce a bit flips, right? It can occur probably one in every 10,000 hours, for example. It's not big deal actually, right? But when it happens, and suddenly you are in your car, electrical car, suppose like Tesla, and then there is some error happens, and there is a car in front of you, and you cannot do a brake, or there's a system error that make they accelerate your car. It becomes terrible, right? So even there's a small probability, the high risk involved. So that's why hard electronics is really important. Another example, as we discussed before, the waste product of the nuclear energy, right? We have a lot of gamma ray and also neutrons. Gamma and neutrons are the waste product of the nuclear power plants that we need to consider. And their intensity are really high there, right? But of course, in the underground experiments, high energy physics, we have so many different kinds of particles there, photons, but their intensity or their amount is not high, of course, right? But still, we need to consider how many times that flip can occur, or the error can occur, how many times in a few hours, for example, something like that. We need to consider that. So how does the radiation can induce electronic damage? So we can classify it into three mechanisms, either by total ionization dose, or we can say TID. TID is a cumulative event, right? Like if just, it means cumulative means if it is just happen once, it won't be a problem. But it needs happens continuously for long time exposures on and high energy, for example, right? And the second is the displacement damage mechanisms. Displacement damage is cumulative even as well, like a TID, but it is more like a more physical instead of ionizing mechanisms. And the third one is single event effects. This single event effects is one time event. This is ionization, but it's only occur once, and probably it can the process only occurs in a few femtoseconds or nanoseconds. It's really quick, but it can damage our devices either permanent or temporary. So let's discuss this one by one. So suppose we have TID here. We have MEOS structure. We have here silicon oxides, and there's silicon junctions there, right? And mostly TID can be induced by photons, but of course, some particles also can induce a TID, but mainly it's due to the gamma or X-ray. So the procedure of this TID is the incoming ray produce the electron hole pairs in our semiconductors, and once the electron hole pairs are produced, the electron can easily drift to the opposite polarity, right? Because the electron can drift faster compared to the holes, while the holes are hopping through the defects inside the silicon oxide, and the silicon oxide we usually have hydrogen impurity, and then it ionizes this hydrogen. Then these hydrogen defects become ionized and move along through the defects, and then create another deep hole trap there, right? So this is the the basic mechanism of the TID. So if we have our transistor, for example, the damage from this TID can be like mostly because can induce threshold voltage shift, noise, and high leakage currents, for example. So the main important parameter for this TID is exposure times, because one incoming ray, for example, it occur for example, like 1 second, it won't give any damage at all. 2 seconds doesn't give any damage. 1 hour doesn't give any damage. Probably like even 1 day or 1 week, assuming the dose of the ray is small, right? So probably it takes years. For example, like if we have our electronics on Earth, right, where we have a low amount of gamma ray or X-ray, right? So the TID even can occur after probably 2 decades or 3 decades, something like that. But it won't be a main issue in the Earth instruments, but it will be an issue in the space. And the second mechanism is displacement damage. Mainly produced by particles, high energy particles. So, but photons as well can induce this DD, but it is through secondary electrons. So there is photons that emit, the photons somehow produce the secondary electrons. Then these electrons hit the particles inside the lattice. So suppose we have incoming particles here. We can say any kinds of particle, basically like heavy ions, neutron, any kind of high energy particles can induce DD. So we have an incoming particles and hit one of the atoms right here. So it creates the vacancy, right? Because the atoms left behind its positions, and these atoms can create another defects like interstitial somewhere, right? And these behaviors also cumulative events. You need a high number of particles or really high energy to induce noticeable damage to the electronics. But mostly there are 4 types of damage that we can see in terms of this defect generations and carriers. So the first is thermal generation of carriers, and the second is carrier recombinations, where this incoming particle can have enough energy to do these recombinations and temporary trappings, as well as reduction of carrier concentration. So of course, this kind of schematic is not really the representation of what happened in the damage here, because it requires a high number of particles that can induce all of these things. But there's a different story if you manage to have really high particles. It can induce a cascade effects. Cascade effects means, suppose you only have 1 particles right here, and then you ejected this atomic from its positions, and this ejected atomics from its positions hit another atoms, neighboring atoms, and the neighboring atoms hit another atoms. That's what we call cascade effects. So these cascade effects eventually create like defect clusters in the semiconductors. This is the schematics, how the cascade create the clusters. The schematics is based on only one incoming particles. Yeah. So as you can see how large the damage can be only from the very high energy particles. So the defect clusters, for example, we can say like silicon materials. For example, you have crystalline silicon there, and this cascade effect can eventually create like amorphous phase and in your materials. And the third one is a single event effect. This is a one-time event. It is quite similar like DD, but a bit different because this is ionization. So you have an incoming particle here, high energy, high mass particles, and then you hit your PN junctions here, creating a funneling. Funneling is the regions where there is electron holes created, electron hole pairs created along the trajectory of the particles. And then once this occurs, the most of the electrons will drift towards the opposite polarities, right? And it's create the high currents, sudden high currents. It's interval in a fraction of nanoseconds only. And it follows by the small diffusion currents because there's some remaining electrons that haven't diffused yet, right? But even these intervals only few nanoseconds, so it can produce temporary or even permanent damage. There are many kinds of SEE that have been reported. These three only the some of the examples. I believe there are about tens of single event damage, right? This single event damage depends basically depends on the case by case basis, based on their circuit layout, not only because of how the architecture or the design of the device itself, but based on the layout mostly. So these two, this SEU and AICTE single event upset induce bit flip, single event transients also. So these two are typically like temporary damage. So only occur once or twice for every 100 hours, for example, right? And it only happens like a fraction of nanoseconds. But it won't be a big deal basically because we have developed some algorithms how to deal with these bit flips. But the worst part is when it induces a permanent damage like single event latch up or single event burnout or get ruptured, right? If you can imagine a fraction of nanoseconds of colliding with a particle can significantly burn up your array or your device, right? It's really concerning for the electronic industries. So these three makeups, suppose in practicals we can classify the damage by these three mechanisms, right? But in practical, we need to consider all of them because we cannot send or deploy our device only based on, okay, we have high TID, but low SEE tolerance, something like that, right? But of course, there are combinations, which one is higher, whether we concern more about TID or we concern more about SEE depends on the environment where we would like to send our device, right? But when we are developing our electronics, definitely we need to consider three things of these mechanisms to deal with. So, for example, in on-ground devices, terrestrial environments, we call it, okay, like the surface of Earth or high altitude environments. The major mechanisms is SE, single event, because as we discussed before, it requires a long time, very long time to induce TID or DD damage to the electronics. So back to the basic questions. Suppose we want to deploy our electronic to space. What are the requirements? So the basic requirements, the main requirements is first lightweight, because we need to send our device, our electronic, as light as possible. As light also equals to as small as possible, right? So device scaling is very important. But it comes to a great cost, because sometimes when we design our device, we have very high dense array, right? So that's also mean high probability to get hit by a particle of photons, right? So that's like a trade-off. The second is low power, because of the spot there's the space in the space, like the probes, for example, interplanetary probes. The source of powers mostly comes from the solar cell, right? So how much solar cell can generate, to be honest, right? It's not much. Efficiency is not much, especially if you consider like very old satellites or very old probes that currently still ongoing mission, right? The efficiency of solar cell is very small. So we need to design our device to have very low power, as low as possible, as long as it can work, right? And it can have enough power to transmit the signals back to Earth or ground stations. And the third is should be resilience. Resilience means not only it is radiation hard. Of course, radiation is the most important things. The second is the temperatures, because in the space we cannot rely on the how to say, like the temperatures conditions is fluctuates really quick, right? So sometimes it becomes really cold, sometimes becomes really hot. So we need to consider this, whether our devices can deviate from its performance or becomes worse over times because of the temperatures, right? Not because like okay, create or we design our system, our device to have very high rad hardness, but it's really sensitive to the temperature, so it won't be useful for space. So all of these categories, these three things are important for space deployments, right? And why it is very important? Because to send this the unit to space, is the cost is really high. Well, for 1 pound of payload, it costs $10,000 US. Right? This is really high cost. So basically, for the manufacturing point of view, basically if you have high Redhat electronics, you have good stability at high temperature, small, high speed, lightweight, low power. The space industry doesn't really care how much you want to sell your device. That's really the interesting things, right? As long as it is reliable up there, and then you don't need to send your replacement unit, so you can avoid or reduce the maintenance cost, right? It can even reduce the total cost of the whole missions, right? That's what the objective is. And we did a great job, right, to shrink our device. We want to make our device small and small, become smaller. So if we compare what we have for data storage in 1956, right, only 5 MB of storage, as huge as our closet drawer. But now we have a 1 TB for our finger, for just a size of our fingertips, right? So it's really great. But even then, we still have difficulty to keep up with the Moore's law. Moore's law is like a trend where the transistor technology can double the density for every 18 months or so, right? But with the present technology that we have, it's just difficult to maintain its track, right? Even though we design some more very interesting architectures like a FinPad. Even now we have get all around, right? So it's really interesting. But still, we predicted that even those architecture cannot keep up with the Moore's law. So there is another point that people keep trying to suggest new kind of devices to overcome this scaling issue. Suppose like we have in the for memory technologies, we have ferroelectric phase transitions, also MRAM, also ReRAMs, and under the spintronics devices, right, that can show some promising to replace this charge-based storage, right? So please keep in mind that our majority of the electronics in the market today is SRAM, DRAM, and flash. Those are technology based on charge-based, or we can say like that, transistor-based architecture, right? So as we discussed before, the problem with the transistor-based architecture is how it susceptible to the secondary single event effects, right? So suppose you have traditional planar box design here, and then the particle or photons hit your device. It can create the charge right inside those PN junctions, and of course it is this design is susceptible to the single event effect and TID, as well as the scale. The scale is not good for achieving high density array. And the second development is by silicon on insulator designs. It's a very nice approach because the oxide layer here isolate the channels. So when the charge build up due to the photons or particles, it has difficulty to drift towards the drain or source, right? Because it's blocked by the box here. But of course, within the box itself can create an additional charge due to the radiations. But the amount is small. But if we compare with the traditional planar block, of course, the SOI designs even much better, right? And I noticed that recent approach that because they can manage to decrease the thickness of this block even thinner and thinner, and somehow they modified these designs to have like secondary gate from this, so it can adjust the threshold shift due to the radiations. So this is a nice way to get Redhat device. The third developments that recently we have like FinFET structures. FinFET structures is really nice, even better than SOE, because suppose you have a particle hit your FinFET, right? There's a small chance to hit the fin because the fin is really small, right? The higher chance is when it hits the deep layer, but it below the layers, right? But even though when the charge generated, it takes a moment to drift through the drain, right? So that's why we say like FinFET effects, FinFET designs has higher SE tolerance and TID compared to the other designs. So what about the new design, like get all around? So far, no one really investigate the Redhat effect of this GAA. Probably it is one of the interesting topic you can work on. So as we discussed before, like basically the transistor-based or charge-based memories really susceptible to the SEE, right? Single event effects because of architectural. So people try to come up with the emerging technologies to replace these transistor-based memories. We have spintronic STT, spin-torch RAM, ferroelectrics, phase change. Now we have the Memristive or resistive RAMs, right? But if you can see here, this is the comparison tables between the structures and as well as the capacity as well as the speed and performance. If you can see here, of course, SRAM and DRAM still the leading performance in terms of speed and also low powers, right? Here, but the emerging technologies tries to keep up with the SRAM and DRAM. They try to replace this. Probably somehow in the future they can replace this, but until now, even the high performance emerging devices still cannot keep up with the SRAM and DRAM. But we are still on track. We are sure someday we can use our emerging technologies as the universal memory. Universal memory means we can use it as the main memory and as well as secondary memory. Main memory means like SRAM and DRAM. Main memory, SRAM and DRAM, they are volatile. Even though they are volatile, but they are high speeds. So high speed is the main requirement for the main memory. Main memory means it requires to process the computation very high speed. Suppose when you boot up your laptop, you relies on SRAM DRAM, not flash or another kind of technology. Why? Because SRAM DRAM very fast. If you rely on flash, probably it takes a few minutes, then you can use your computer. So it is too long. That's the one major reasons. Among these emerging technologies, we can say the MRAM is the best in terms of the performance, right? It can almost replace the SRAM and DRAMs. The endurance are really long, and the speed's really high, and the energy is also very low, right? And compared to the other of emerging devices. Compared to ReRAMs somehow in the position like well acceptable endurance, as well as the speed, as well as the energy consumption is a bit acceptable, right? But the main things what the resistance can offer is it can be free of transistors. I mean, free of transistors mean it doesn't need as a transistor as the select device, right? If you can see here, the basic structures of these devices here, each of these devices requires transistors as the select device. But for the RMs, we can replace the transistors with the diode, for example, general diodes. So in the space or nuclear application points of view, the less transistor you have, the better it will be for those environments. So what's the damage for the SRAM? SRAMs consist of 6 transistors. So suppose you want to store your information, you require 6 transistors. So the feature size is up to 150 F square. So once the SAE occur, there's a bit flip happens in the device, right? So for the SM, if I'm not mistaken, there are 2 nodes. So each node store the informations. So if the particle is strong enough, it can flip both of the nodes. And second is DRAMs. DRAMs a bit better because it only requires 1 transistor and 1 capacitor, and the feature size only 30 F square. So for the DRAM, it stores information in the capacitors. It can also use work as a multi-bit memory. However, when the SAE occur in these DRAM structures, it can induce deviations from these bits, right? Suppose from it, the position is 1-0 state, and when the particle strike, it can deviate to 0-1 or even suddenly goes to the 1-1, for example, right? That's the bit flip procedures there, and it can become worse even when we try to scaling down these structures. When we try to scale down this DRAM, of course we need to scale down also the capacitors designs, right? As the capacitor getting smaller and smaller, it become more easier to modify or alter the charge inside the capacitors, right? So a tiny amounts, even tiny amounts of SEE can induce a damage to the small scale capacitors. And the same things happen with the flash here. The flash is even better in terms of the architectural point of view. It only requires 1 transistors, right? And it stores the informations on the floating gates based on the charge. It's also similar mechanism like a DRAMs, where the radiation can induce voltage threshold shift here. So it can induce an error when you read the informations there. So if you can see here, as long as you have transistors, you cannot put the scaling down the device, right? Even though you try to make out with only 1 transistors only, the feature size cannot go down more than this number, right? So That's why DRAM, SRAM, and flash they are struggling to keep up with the trends of the Moore's law. So the emerging memory technologies can give some promising idea, but in this case, we roll out ferroelectric and fast change SRAMs for the space and nuclear applications. Why? Because first, the ferroelectrics is sensitive to the contaminations. It's not really fab friendly, and the second is the PCM is because PCM's mechanism is controlled by temperature, right? When you control, when you modify the crystal into amorphous or vice versa, phase transformations, where you get the on-off states, right? So suppose you send your PCM to the outer space or even to the nuclear reactor, it is not good because it can suddenly just change the crystallinity or the phase of your RAMs, right? So we roll out these two technologies. So one of the best options is MRAM, as we discussed before, because the MRAMs shows very high performance, the highest even compared to the other technologies. The mechanism of MRAM basically consists of the three layers. The structure consists of three layers. We call it as a free layer, insulating layer, and reference layers, right? So the reference layers, the magnetic polarity is fixed, but for the free layer, where you change the magnetic polarity can be changed either by magnetic field with this design, or either by currents with this one STT design, right? But there's a problem, because as we mentioned before, the MRAM still need transistor, right? Still need the transistors as the select device, right? Suppose you have MTG device here. This is based on the schematics. You have neutrons hit your device here, right? So basically, when neutron hit your device, because of the very small architectures of these MRAMs, it's not really induce very large charge here. If you can see here, basically the free layer and reference layer only few nanometers. Even the insulating layer can be down to only 1 nanometers. Right, it is really dense, basically. So, but it becomes problems when the neutron hits the deeper layer components, right? So where this charge drift through back to your device and induce a bit flips. So that's for the ICE. What about the DD? DD also the main challenge for the MRAMs, because as you can see here, like in the MRAM architectures, the barrier layer is really thin, right? The insulator layer is really thin, approximately only 1 nanometers, only 10 angstrom scales, right? So this is the TM image of the PDFE, MGOFE, MRAM stack. It irradiated with 150 kilo electron volt of nitrogens. So if you can see here, so once the DD occur, the atomics of from these neighboring layers, in this case of iron. So the iron will mixed with the MGO, right? Because the MGO insulator layers are really thin, so the mixture of this mixture composition can happen due to the DD. That's the damage can occur. But even then, the probability of DD, especially when you use in the environments, is not really high. But still, they give considerable damage when it happens. And the last we have is memristors. Memristors, we can say memristor is an hard rock element because it is intrinsically hard by design, right? Why is that? Because first, because the simple structures. I noticed, I think yesterday, that the panel already discussed the basic concept of the memristors here. As you can see, memristor can have two main mechanisms, either cations or anions. And of course, there are another kind of concepts like fully electronic trap, something like that, right? So mostly the acceptable concepts are cation-based, anion-based. So both of cation and anion-based are due to the redox process inside the memristor cells. For the cations, the redox occur for the mobile metal. For example, if you use silver, nickel, copper, for example, they are quite mobile. You can ionize and create the conducting filaments, or we can also say conducting pitch. And then with the opposite polarity or similar polarity, you can rupture these filaments. And other things is if you have intrinsic defects inside your cell that creates the filaments. So suppose most common mechanism is oxygen vacancy mechanism that creates this the growth of the filaments, as well as the combinations with oxygen ruptures the filaments, right? So the beauty of this architecture is you don't require a transistor as the select device. You only need to have a diode here. Well, you know, diode is also like metal insulator metal structures, right? So basically, you stack two structures, the same structures, right? So what is the total thickness of this memristor and selectors? It is even quite small as compared to the when we have one memory and one transistors configurations, right? Because memristor and selectors, the configuration is just similar. Probably a selector has the same thickness or a little bit thicker than a memristor. And if we compare the TID resiliency between various memory devices, we have a NAND flash here, MRAM, and CBRAMs. CBRAMs like the cation base and ReRAMs here. Some people also say VCM or OXRAMs, etc. If you can see here, both ReRAMs here, ReRAM, CBRAMs, or VCM, or whatever you call it, they have, all of them have very high resiliency towards high dose of radiations. you can see here, if you have like NAND flash, it can only induce error with tens of kilorads, right? So so we can simply claim that memory stores really have well, immune to the single event effects, right? It is immune. We can claim that. And it's also have like high tolerance towards DD. It requires high fluence of the high particles to induce damage, and also high TID tolerance. It can sustain up to several hundreds of kilograms. Even current report, it can sustain up to several gigagrays, right? Grays, one grays means, but probably you confused about the units of here of rad and grays. They are similar because 1 gray equals to 100 rad. Yeah. So what happens with the memory stores during TID or DD? So even though we say a memory store is really high tolerance towards the TID and DD, but at some point it can also induce damage. So this is an examples with the TIN hafnium oxide PT stack structures. We can see here, like after you expose the device up to 5 megarad, you can induce oxygen vacancy inside the cells. So it creates disruptions, maintaining the HRS or LRS, right? Because of this contribution of the new generated defects. So if you have a long exposure of TID and DD, yeah, you increase the leakage currents, and yeah, of course, reduce the resistance. You increase the leakage currents means you also reduce the resistance of the stack, right? It can be a problematic issue if you want to have a long time retentions, right? If you want to achieve 10 years of retentions, but these defects are generated after TID or DD exposures, probably your device can induce a bit flips after 1 year or 2 years, something like that, right? And similar things happens when people try to investigate what is the impact of TID and DD for the analog performance of the memory stores, right? I forgot to mention one of the interesting capability of memory stores is the analog behaviors, where we can utilize this analog behavior for AI hardware. So if you can see here, basically when you try to irradiate your memory stores, it can induce the intrinsic defects. One of the things is oxygen vacancy. The consequences of the introductions of this oxygen vacancy, you induce higher conductivity towards your memory stores, to your cells. So in this curve, you can see this is the potentiation behavior of the tantalum aluminum bilayer devices. If you can see, it is highly dependent on the radiation dose, right? From the small radiations, 3 kilorads up to 59 kilorads. It increased the conductivity of this. Well, in terms of circuit level or system level, this kind of deviations is not really concerning, because we can simply adjust the circuit or the systems or the algorithms uh, to make up with these deviations. Well, we already discussed the two examples of what happens with the oxide-based memristor when a TID and DD occur. But when we use chalcogenide material for our switching layer in our memristors, the result is quite opposite compared to the oxide one. Because when you try to irradiate your chalcogenide-based memristors, instead of increasing the high leakage, it decreases the leakage. Here, you increase the resistance of your device. Why is that? Because chalcogenide tends to more sensitive to to radiations, because the radiation can induce phase transformations in your chalcogenides. So basically, these two behaviors depends on the applications. Is suppose if you want to use it as a storage, of course, it can be concerning at some point, but every challenge there is of opportunity, right? If you can see from these results, right? There is some sort of sensitivity towards radiations. So we can even more explore this memristor device, this result, right? This tendency towards the radiations as the sensor, right? So memristor could be the future radiation sensors. There's one opportunity that we can exploit. As we mentioned before, the memristors can be used beyond storage, right? So it's not only can be used to store informations, but recently explored for various things, for chemical sensor, temperature sensor, different kinds of sensors, right? Light sensor, touch sensors, right? The combination of these sensors can make up electronic scale or health monitoring systems, right? It is very nice. And another important things of the applications of the memristor is brain-inspired computing, because the memristor can work analog, right? And it's not like transistor based, it's often work as digital. But recent development, of course, some people try to make a transistor work as analog as well. But in my opinion, it still cannot be compete with memristor, because the analogous behavior of the memristors is quite promising compared to the other designs. So these analog designs can be useful to make AI hardware accelerators. So back to the sensing capability. This is another applications that we mentioned before about the sensing capability. There is one report that already explored. This one based on the switching times. So suppose you expose your device with some radiations, and then you evaluate the number or the value of the radiations, how high the exposure is, and based on how fast your device switch. As you can see here, the before radiation, the switching time is quite long, right? hundred of seconds up to 800 seconds, right? So after the radiations, the switching times becomes less and less, as we discussed before, because it induces more intrinsic defect, right? For example, this is oxide. It should be induced. It should induce like oxygen vacancy inside, where oxygen vacancy induce leakage. When we induce leakage, it become more easier to form the filaments, right? That's kind of the mechanisms here, and they successfully patent these designs for the radiation sensing. But of course, if you can see, like the previous result that we discussed, there's different tendency with these potentiations, analog behaviors, right? Also different tendency of this resistance, right? All of these things, or even the voltage operations, all of these things can be exploited to sense radiations. That's the beauty of it. Another applications for the memristors is like, if we can go down to the more we can go down to simpler structures, right? For replacing the resistor with the memristors in the simple passive circuit, for example, right? So you can you have the passive circuit. Once you replace the resistor with the memristor, you can somehow tune these circuits, right? So you don't need, in the end, you don't need transistor to as the tuning device, right? This is another benefit. When you minimize the number of the transistor, this means you also minimize the number of array level, or the size of the device. You minimize the number of the device, means also you create low power circuits, right? Yeah. So all of these things we can. So basically, the potential of memristors is quite endless. You can give your creativity, where you can exploit the memristors for your circuits, right? So all of these things make up the 3 points that we discussed before: lightweight, right, low powers, and also resilience. Those are the important things for the space and nuclear environments. And this kind of approach, one of the examples for programmable analog filters already patented, right? Yeah, this is very interesting. Another idea is to solve the problems. We have that high, well, we can say very huge data sphere problems. It is expected the total data sphere, the number of data that created by well, we can say that by on Earth or on ground computers is up to 175 zettabytes, right? 1 zettabyte is equal to 10 to the power 9 terabytes. So you can imagine that. So what can we do about this, right? So so if we cannot do anything, we just keep requiring more and more data storage, larger data storage and data centers, right? Where you want to save all of your pictures or videos or documents, right? Especially people now use almost every people use Facebook, Twitters, etc. Like where they store the information in the cloud servers, right? So it is quite concerning. So that's how the memristor can play a role. And another things that we need to mention, right? It is really important is in the outer space. It is difficult to achieve AI hardware in the space. Why? Because the recent technology still used as we discussed before, still use a transistor base, right? So it is difficult to make a AI hardware accelerator on the space. So why we require AI accelerator in the space? Mostly because of the data transmitting reasons. Suppose you have a satellite. Well, I can pick up an example like Hubble telescope, for example, right? Hubble telescope takes a bunch amounts of data or images from the space, right? But the problem is with this telescope or any kind of probes or any kind of satellites in general, they cannot sort out the information. So which kind of data is noise, which kind of data is important, they don't know, because they don't have the computing power, they don't have the capability to compute these informations, right? So all of those data transmit back to Earth. So once the ground station receive it, it transfer to the cloud server. The cloud server then analyze the data and tell the user, okay, this is a noise, this is the important data, and then the rest you just discard the rest, something like that, right? So suppose you have a memory stores, good analog memory stores, low power, high dense memory stores, right? And then you can manage to create a good AI hardware accelerator embedded to your satellite, for example, up there, right? So can you imagine the capability that you can have, right? So so you don't really concerned about the bandwidth anymore, right? Something like that. So it is one of the interesting area that whole country is working on today. So as the remarks today, so we discussed that all types of the whenever you use transistors in your circuits or systems, will be prone to the SEE, right? And then it is difficult to scale the device down or the total arrays down, right? Because it's difficult to keep up with the Moore's law, right? MRAMs is not affected by SEE, but still affected by DD. The problem is MRAM is not really favorable for the space or nuclear because it requires the transistor as the select device. That's the major drawbacks there. And memory stores probably, well, the performance is not as fast as SRAM, DRAM, or MRAMs in terms of energy consumptions, right? In terms of the speed also, right? But these combinations make up good combination for the space and electronics, space and nuclear electronics. Because of the one thing is because of the Redhat architectures, and the second is low powers, right? And it is also lightweight. So these three important things that space and nuclear deployments require. And the other thing that we need to emphasize that Memristive is immune toward the SEE, right? So because when we use Memristive, we can minimize the number of total number of transistors in our systems. So Memristive will be good chance to deploy for the future electronic vehicles, right? Or the data centers, cloud servers, right? Or on ground station. Yeah. Well, basically this is conclude my talk. But before I finish my talk, I would like to share one thing that currently our university, we are hiring PhD students to join the radiation hard electronic groups. So there are several positions here we offer, like nano device engineering, where you fabricate your 1s1r array crossbar structures, and then we exploit the radiation tolerance and also exploit the sensitivity of this device. And the second is whether you are good at coding probably or simulations. You can work on these materials or electrical compact modeling, where you can evaluate how the damage of the memristors in terms of the cell-to-cell basis, right? And another topic is neural network modeling. So you evaluate how our memristor device, our array, whether it is good enough for neural network, and whether you can exploit or explore mitigation algorithms where they suppose like there is a TIDA or DD damage. The electrical is deviate from its original states. For example, you can develop the algorithms how the neural network can still process good accuracy, right? So for these projects, we collaborate with several industry and universities in the UK, Italy, Belgium, and United Emirates Arabs. So basically, this is a very interesting project. So suppose if you are accepted in our group, you can visit all of these collaborators, and then where you can do some extend experiments, real experiments that you close with industry. That's a very main important points here, right? And the one of the industry that we collaborate with Surrey satellites here. The idea is because we want to deploy our memory store systems toward to low Earth orbit. So the main objective is you do a neural network on the space and low Earth orbit. So the Surrey satellites will help us to deploy our systems with their satellites deployment. And the other things is, suppose if you're more interested in the radiation test, you can visit Belgium, for example, where this our collaborators in Belgium also have a strong network with the CERN Large Collider, right? And if you also interested in like shielding technologies, we collaborate with the Redhat devices in Italy. So there's a broad opportunity when you if you study with us. Well, another things that I would like to mention is like as we are in the University of Southampton, so we can proud to say that we are the number ones in the electronic field. We have high-end advanced clean room facilities. We have many kinds of types of the plasma and etching process, right? We have the wet rooms, very good wet rooms, and also very good even deposition process. As you can see, this is our this is one of our I forgot the name. Helios sputters. This is one of our sputter systems. As you can see, you can load up a lot of wafer at once, right? So it's just like a large scale or industry scale process. And of course, we also equip with good characterizations, materials, and electrical characterization. You can visit these links, or you can contact me directly if you are interested. So basically, this is the end of my talk. Feel free to ask questions. Thanks.
Yeah, thanks, Dr. Firman. You have taken, as you told, you may take maximum 1 hour, but you have taken only 1.5 hours. That's great. So whenever you start speaking, you are unable to, you already forgot the time. That's great. Okay. If you have any questions, please ask very short questions as possible. So maybe 1 or 2 questions we can take. Very short question. I like to request all of you, please ask any short questions. So I hope Firman, you will get some students from these participants, because there are a lot of students are also there. So I hope you will get some good students, whatever you are looking for. Maybe you will
yeah, hopefully.
Yeah, you just share your link. I will share with my other group also.
Yeah,
all the participants.
thank you.
Yeah. Okay. Yeah, Devanjan, I think you wanted to ask something. Please ask.
It's a very nice talk, and it's a very cutting edge research topic you are working on, and it's a very nice topic. I mean, you can get lots of idea about this thing. I have one question regarding your MOSFET based structure. That is the MOSFET. You have shown that there is a funneling due to the dose. So that means specific question is that how can you control the substrate bias instability that is induced by the current due to the funneling?
I'm sorry, once again.
So my question is that how did you control the substrate bias instability due to the funneling induced current, which is due to the dose? So how did you control that? Because you know the substrate should be in zero bias for the operation. So as there is a current which is due to the funneling, so how did you control that thing?
Oh, you mean how to mitigate this SE damage?
Yes.
Yeah. So basically, there are some way, like some people like make up like secondary gate or give some bias, constant bias to minimize this effect. But mostly SEE is difficult to mitigate in terms of device level, because the incoming particles deposit large amounts of energy and the fractions of nanosecond or femtoseconds. So there's not enough time to mitigate these mechanisms. That's the main problem with this transistor base.
Because this is the dose means is a very high trajectory, and the very huge number of types particles are there. So that means the current should be very high, and that inevitably increase the substrate current, and that means it will give you the more amount of power consumption. It leads you to the high amount of power consumption.
Well, it can. Well, we cannot say it is an effective way, because this kind of damage is really really can induce very high currents, right? So even a single particle can burn out your device directly. So the best way to mitigate the array, the circuit, is to minimize the number of transistors. That's the optimal solution.
Okay, thank you very much.
Any other questions? Yeah, I think there are no more questions. I think it's already late for Firman also. He need to work something. We are also late. Well,
Yes.
so I like to request Dr. Geeta Priyadarshini to give vote of thanks and the last thanks to Speaker Dr. Firman Mangasa for his nice and very attractive talk.
Thank you, Dr. Debashish Panda, for this opportunity. I would like to thank Dr. Firman Simanjantak for giving an excellent talk on Memristve's technology for space and nuclear application, which is quite fascinating for us because we have been exposed to these kind of devices only for data storage and chemical sensors, as you have talked. But it's the irradiation effects or radiation effect, to be particular, has not been has been the scope of study in this particular part of the country. So I think you have given us a very broad perspective how radiation could influence the devices, which is going to affect the performance, and and also you have given how the world is going to be transformed in a little later with all sort of data storage, and how this impact of these radiation induced effects on the devices will play a major role. So I think this was a kickoff presentation for all of us. I think all of my participants would agree. And I take this opportunity to thank you for this wonderful talk, which was really, out of the box for us. Thank you very much.
Thank you very much, Dr. Geeta, Dr. Panda. Thank you very much, everyone. It's my pleasure.
Thank you, Dr. Geeta. Thank you, Firman, for accepting our request. With this, I'm closing this session now.